In this video, we are going to look at the two-dimensional problems of relative velocity. That is when bodies are moving in a plane. So the problem that we are going to deal with in this video is a typical relative velocity problem, where we have raindrops falling vertically downwards and a cyclist is moving in the horizontal. Instead of the cyclist, you could have a car. Okay, you can have a man walking on the horizontal with a certain velocity or something like that. So let me read the question for you all. Raindrops are falling vertically downwards with a velocity of 25 kilometers per hour, and a cyclist is moving on a horizontal road with a speed of 15 kilometers per hour. Find the relative velocity of the raindrops with respect to the cyclist. With respect to the cyclist, meaning the cyclist is the observer. Remember that. Also, these velocities that are given, the velocity of the raindrops being 25 kilometers per hour and the speed of the cyclist being 15 kilometers per hour, these velocities are with respect to a stationary man or with respect to the ground, remember. That is, when a stationary man looks at the raindrops falling, he sees the raindrops falling vertically downwards and with a velocity of 25 kilometers per hour. Likewise, when the stationary man looks at the cyclist, he sees the cyclist moving along the horizontal with a speed of 15 kilometers per hour. But this scenario of the raindrops falling, what does it look like to the cyclist who himself is moving with a speed of 15 kilometers per hour? Okay, that is what we are required to find in here. So let us suppose that this vector or this arrow represents the velocity of the cyclist, whose magnitude is 15 kilometers per hour. Likewise, this vertical vector represents the velocity of the raindrops, whose magnitude is 25 kilometers per hour. Now, keeping the magnitude and direction of a vector fixed, we can take that vector anywhere in space, because that is eventually going to give us something called an equal vector, remember. But, like I mentioned, we have to keep the magnitude and direction of the vector fixed. Likewise, keeping the magnitude and direction of this vector VR fixed, what we do is we take this vector at this point, such that we get a scenario like this. So this is your VC, the velocity of the cyclist, and this is your VR, the velocity of the raindrops. Mind you, here the direction is fixed, the magnitude is also fixed, so therefore this VR and this VR are equal vectors. Now just an information for you all. Whenever you get a problem like this, a relative velocity problem, you'll be given two velocities, of course. So you can straight away jump to a picture like this, rather than drawing individual vectors, showing individual vectors like this. I have shown individual vectors over here just to make you understand, just to give you an idea about the velocity of the cyclist, the velocity of the raindrops. Okay, you can straight away jump to this scenario. This is the cyclist moving along the horizontal, its velocity, and this is the raindrops falling. So you arrange these two vectors in such a way that they always start from the same point. So straight away, like I said, you can jump to this picture. Now we know that the relative velocity of raindrops with respect to the cyclist is given by VRC, that is velocity of the raindrops as seen by the cyclist, which is velocity of the raindrops minus velocity of the cyclist, which can also be rewritten as VR plus or minus VC. In other words, we are simply to find the resultant between vector VR and vector minus VC. As you can see in the picture, this is vector VR and this is vector minus VC. So we are to find the resultant between these two vectors, so to say. And the resultant between these two vectors is given by the parallelogram rule, which says that if we have two vectors starting from a point, then the diagonal of the parallelogram starting from the same point is going to give us the resultant between the two vectors. To give you an understanding of this picture first, we have a cyclist moving with a speed of 15 kilometers per hour along the horizontal, and we have raindrops falling vertically downwards at this speed. So what the whole scenario of raindrops falling is like for the cyclist, that is what we want to know. And what it looks like to the cyclist running with this speed is that it looks to him as if the raindrops are coming at this angle towards him. And that is exactly what happens in reality. If we are inside a car moving with a certain speed along the horizontal and raindrops are falling, we see raindrops coming towards us at some angle. So this is what this picture tells us. So the only thing that is left now is to find the resultant vector VRC. Resultant vector meaning we need to find both its magnitude and direction. Now, according to parallelogram rule, we know that the magnitude of the resultant vector is given by modulus of r, which is square root of a squared plus b squared plus 2ab cos theta, where theta of course is the angle between vectors a and b. So magnitude of VRC is given by square root of VR squared plus VC squared plus 2VR VC into cos of 90 degrees, because the angle between the velocity of the raindrops and the velocity of the cyclist is 90 degrees. So modulus of VRC is square root of 25 squared plus 15 squared, and the third term is 0 because cos 90 degrees is 0. So this thing comes out to be 29.15 kilometers per hour. What we understand is simply that to the cyclist it seems that the raindrops are falling with a speed of 29.15 kilometers per hour. To a stationary man, raindrops are falling with a speed of 25 kilometers per hour, vertically downwards. But to the cyclist, it seems that the raindrops are coming at this angle with a speed of 29.15 kilometers per hour. So to the cyclist, raindrops are falling at a greater speed. And what we now need to find is, we need to find the value of this angle at which the raindrops are falling for the cyclist. To get the direction, let us consider this angle to be alpha. That is the angle which VRC makes with the vertical to be alpha. Therefore, the direction of VRC is given by tan alpha is equal to b sine theta divided by a plus b cos theta, which is the formula we get for direction from the parallelogram rule. Since we've chosen this angle to be alpha, therefore VR is our vector A and minus VC is our vector B. So that is why I've written tan alpha is, instead of B we have minus VC, sine of 90 degrees, since theta, the angle between the two vectors, is 90 degrees, divided by A is VR, B is minus VC cos 90 degrees. Now cos 90 being 0, so therefore this term, the second term in the denominator, becomes 0, thereby we get tan alpha is minus VC divided by modulus of VR. So tan alpha is 15 kilometers per hour divided by 25 kilometers per hour, or alpha is tan inverse of this, and thereby we get alpha is 31 degrees. This comes out to be 30.96, something like that. So, but I've taken it to be 31 degrees. So finally we write, therefore it seems to the cyclist that the raindrops are falling at a speed of 29.15 kilometers per hour at an angle of 31 degrees with respect to the vertical. You have to mention this. You cannot put a full stop over here. At an angle of 31 degrees full stop. No. Because you have to tell 31 degrees. This angle is with respect to what? You have to mention that. Remember. Now I have this problem for you all, where in say for example we have two ships. Ship A and Ship B. Ship A moving with a velocity VA having magnitude 10 km per hour, and Ship B moving with velocity VB having magnitude 20 km per hour. And let us suppose that the angle of inclination between the directions of movement of these two ships is 60 degrees. So what you need to find is the relative velocity of A with respect to B, and also the relative velocity of B with respect to A. Let me show you the physics part to calculate the relative velocity of B with respect to A. Now VBA, as we know, is given by velocity of B minus velocity of A, or rather the resultant of VB and minus VA. So this is VB and this is a minus VA, and the resultant between these two vectors is given by the diagonal of the parallelogram starting from the same point. So this is your VBA, which means when your friend inside ship A looks at you inside ship B, or rather your ship is moving in this direction.